before we get started, I think actually most people in this room already did reply that, but let me recall once again, so that if you need the grade, you need the final to do final project. So final grade is implied by the final project, not the other way around. And so then you should send me an email by today telling me that you wish to do the final project. So we then discuss what are the topics. I have some topics that I've given in the past, and maybe we can also discuss some other topics if you have some other ideas. So far, at least maybe four of you or so have replied. So I don't know how the question was mostly how many people are actually interested in doing this. Okay, so good. So what we talked about last time was the entropy criterion. And entropy criterion tells you that you can detect the triviality of the Poisson boundary by the entropy. So you start with G mu, a measured group. And again, we assume that the entropy of mu is finite. And then we can define the Albert's entropy as H mu is the limit as n goes to infinity of H of mu n divided by n. So we know that this limit exists. And so the theorem is that under these assumptions, let's also assume that if you take the support of mu, you take the semigroup generated by the support of mu is G. So we see that the measure sees the whole group, so there are no issues like that. Then we want to say that the Poisson boundary of G mu is trivial, meaning that there are no non-constant harmonic functions, bounded harmonic functions, if and only if the asymptotic entropy is 0. So again, this is a very strong fact, because to identify the Poisson boundary, we have this theory of partitions, so it's very indirect. On the other hand, computing the entropy, well, it's not always easy, but it's much more concrete thing that you can do. Okay. So we saw last time a sketch of one proof, and today we're going to see another different proof using partition. So this proof is the proof of Kajmanovic and Vershik in '83. And it's based on, again, on partitioning the space of sample paths. Okay, so we can define, so we consider the space omega p, the space of infinite paths. And then we introduce sequences of partitions. So we say we have the head partition, alpha k. So of course, introducing a partition is the same as introducing an equivalence relation, because so we consider two sample paths to be equivalent according to the alpha k partition if they are the same at the beginning. So if W yeah, Wj equals Wj prime for all j at most k. So here we have two paths that start in the same way. We don't know what they do next. So they start same way, then they might diverge, that's fine. And also we recall that if you take the n+1 partition, so the partition where they share the first n+1, well, this partition is finer than alpha n. Right? Because here we're imposing more conditions. Then there's the other partition, which is the tail partition. Eta k, for each k there is a different one. And this partition is like that. So you consider Wn in the same class of Wn prime if Wj equals Wj prime, but at the end of the path for j at least k. So this is the sort of dual situation where we have paths which can start however, but then they will coincide later on. So this is W1, W2, W3, W4 equals W4 prime, W1 prime, W2 prime, W3 prime. Okay? So here we note the opposite. So if you do eta n+1, this is coarser than eta n. Because we remove the requirement that they are the same as step m. So, and now the tricky thing is to define the coarsest of those, which is called the asymptotic pair partition. We'll call it eta infinity. And this is the coarsest, the infimum in the language of partitions of those partitions of eta n over all n. So this is the, what is this? Again, this partition is coarser than all of those. But it's the finest partition that is coarser than all of those. This symbol is the same. So this is the finest. However, there's an issue here that when we pass to this, if we want a nice partition in the sense of this measurable partition, we have to say this is the finest measurable partition. Coarser than all eta n. So again, this measurable means that this is, say, countably separated from what we said last week. So we have to, so we don't just take, we don't just take the classes, but we might need to join certain elements in the same equivalence class to make this partition. And so now the triviality, the fact is the following, that so the Poisson boundary is trivial, so triviality of the Poisson boundary is equivalent to eta infinity being trivial. Meaning that every class has measure 0 or 1. And again, there is a little bit of thing that I sweeping under the rug is that here when we define the tail partition in this way, we're taking the synchronous partition. So we are saying that the two paths coincide at the same step. While the way we defined it at the very last, at the beginning, was that we were also allowing two paths to coincide, but after a different number of steps, like say 3 steps for Wn and 4 steps for Wn plus for W prime. However, on a group, the quotient of omega by these two partitions is the same. So we can think of eta infinity also as the partition that gives rise to the Poisson boundary. So basically, again, Poisson boundary is trivial, meaning that there is no tail event. We can think of this as being tail event, only depends on the tail. Okay, so any questions? Okay, so now what is nice about this approach of Kamenovich and Vershik is that you can sort of do some computations of this entropy and conditional entropy as well. So let's do that. So again, we have also the conditional entropy, which we already mentioned. So if you're given psi and eta partitions, we define the relative entropy as minus the integral of log, and here is the conditional measure. So measure of psi of x intersect eta of x divided by measure of eta of x dmx. Right. So again, eta of x is the partition element that contains x. So this is the conditional measure. And also we note that h psi condition on eta equals, sorry, as I said incorrectly last time, equals eta of psi if and only if psi and eta are independent. So what is independent means? Well, is that the measure of eta and psi is the product. Yeah, the measure of the intersection of two pieces is the product of the measures for almost all x's. Okay, so the idea in the proof is that we want to know something about this partition, and to say that this is trivial, well, trivial means it's independent of anything, of everything. And so if we show that this tail partition is independent of alpha k for each alpha, since all the partition generated by all the alphas is just a Borel partition, it's like every measurable set, then you're in good shape. So that's what we would need to do. So the most important part is the following proposition, which is the following. So we define Hj as the entropy of mu j, as we done before. So for the here, now we are back to the run walk. So, and the claim is the following, that h of alpha given eta n is the following: is k h1 plus h of n minus k minus hn for 0 less than k less than n. So remember, the idea is, okay, you are the first k steps of the walks, and here you are the steps from n onwards, right? So your walk at some point, sort of, you know the end of the walk, and then there's a gap, and now you want to know you want to know the entropy of knowing the first k steps once your conditions are ready to know in the tail. So this is known. Okay, so this is the most important equation, and this unfortunately is not hard to compute by thinking about this random walk. So again, you see that Wn is written as G1 GK. This is WK. And then there is GK plus 1, Gn, let's call this G. And this part, well, just by doing the ratio, is WK inverse Wn. Okay. Straightforward. Now the question is, what is the probability they induce, the relative probability? So what is the probability? So what is alpha k? What does it mean to predict alpha k? It means you know the first k steps. Okay. So what do we want to predict? We want to predict that W1 equals some given G1. W2 is some G2. WK is some G. Okay, maybe G is maybe not the best notation here. So, but anyways, given that, okay, let's given that Wn equals G, right? And in fact, so predicting the first WK is the same as predicting the first GKs, because G1 is W1, W2 is G1, G2, and so on. So let's write it like this. The prediction that G1 equals a given H1, sorry about changing the notation, GK equals HK. So I'm fixing H1, HK, and I'm fixing the G. So I want to say, okay, suppose that we know that after n steps we are at G. What's the probability that our first k steps are H1, H2, HK? Okay, so now we can compute, because it's a random walk, so it's not really that complicated, right? So, well, in the denominator we need the probability that Wn equals G, like in any computation of conditional probability, and in the numerator we need the probability of the intersection, right? So what's the probability of the intersection? Well, again, we have to specify this first k, and then we specify this jump, and that's it, right? So because once we know the first case and we know the nth step, well, we know that this is just the ratio of those. So this is like the following. The probability of G1 equals H1 is mu of H1. The probability that the second increment is H2 is mu of H2. So forth. So this is mu of HK. And then the last thing is that we want just the probability, well, that the n minus k step equals what? Well, it has to equal the ratio, right? So this one has to be G1 GK inverse G. So H1 HK inverse G. Do you agree on this? Because this is the first part of the walk, which we know. This is the last, the end point. So the second piece has to be like that. Okay. And so now we can just compute, right? So what is H? Yeah, so H alpha k given eta n is precisely the integral of this over all possible choices, right? So we're integrating the log of that probability. So it's minus the sum and you see the only probability that matters is the distribution of the first n steps, even though this is technically an integral over the whole whole path space, but well, everything happens up to step n, so it's a discrete thing. Right? So what do we have here? So we have minus log of mu of hi. So this is h from 1 to k as a first step. And then the second step is this one, minus log. Well, what is this? This is mu star n minus k. Right? Of this one, of hk inverse h1 inverse g. And then we have this one. Well, this is simply mu n of g. Right. So plus log mu n of g. And then we have to again sum once again, because we have to integrate. Right. So maybe we could, okay, maybe let's say that, let's write it again as an integral, like that. And the integral is the p of omega technically. But then, of course, everything only depends up to the first n steps. So in the end, it's going to be a finite sum. Okay, so let's see. So it turns out that literally, this is what we want. This formula was what we wanted. So let's see. So you have the integral of mu of h. So this is just one step, one increment. So this if you integrate this, you get H1. So again, so this is, if you integrate, you get literally K times H1. Now, what about this? And what about that? Well, the last one is clearly Hn minus Hn. That is pretty obvious. The only one which is maybe slightly less obvious is this one. So because we are integrating. Yeah, we are integrating twice, but then here again, if you think about it, this is also a walk. So if G is the n step of the walk, this is literally just the n minus k steps of the walk as well. So because this is a run walk, so everything is, the increments have the same distribution. It's this distribution of increments is stationary. So this is indeed h of n minus. So right. So this is the most important formula. Once you understand this formula, then you understand that, well, you want to know what happens if we let eta n go to infinity.
I'm a bit confused by the signs.
Yeah.
Wouldn't it be like, why is there a minus log in front of v star n minus k? Wouldn't it be minus log v star n and g? You're taking log of the previous line, right? And summing that? Or...
Right, but this is in the denominator, isn't it?
Yeah, so it's good minus log, right?
Yeah, but then in the entropy formula, there's a minus log at the beginning.
Right, so you already put that one in. And then wouldn't the first two have the same sign?
Yeah, this is minus. This is minus. And this is plus.
Right. Okay.
Right? Is that a problem? Let's see. Did I write something wrong there? So, I see. So, oh, this one, maybe that's the problem is here, maybe. Or no, it's correct, right? Yeah. So this term and this term have the same sign, and this term has the opposite sign, which is the same as here, right? Positive. Right? No, what's the confusion?
Sorry, the first term and the second term have different signs, right?
Why?
Oh, no, the negative sign. I get it.
Right. So this is in the numerator,
yeah,
which gives rise to this. This is also in the numerator, which gives rise to this, and this is the denominator, which gives rise to the other. Okay. So, okay, very good. So that's the most important point, because okay, now we take the limit. So now h of alpha k with respect condition at eta infinity. So here's why the magic happens. Is because you see, this is just the limit as n goes to infinity of h alpha k conditioned at eta n. So we now recall that eta n plus 1 is coarser than eta n, right? So every time you're conditioning on something coarser, so this is increasing. So there has to be a limit. And in fact, if you define eta n, so remember that eta n is coarser than all of the eta infinity is coarser than all of the eta i's. So this is at least the limit. But then it turns out that that has to be equal to the limit, because this is the finest partition, which is coarser than all of those. So somehow this thorny issue about taking the measurable envelope here just comes down to a limit in the entropy. So that's a much more concrete and easier thing to check.
Sorry, I have another question.
Yeah,
Why is the entropy continuous this way? So, I mean, I know eta is like like kind of the courses of all the eta n, but why?
right. So first of all, the limit exists. Yeah. Yeah, this is not completely obvious. I mean, it's a property of this measurable partitions. But right, so first of all, what do we know? So this one tells you that h alpha k given eta k plus 1 is to be bigger than this. You agree with that? Because right. So also we know that this is closer than eta infinity. So definitely, yeah, sorry, not k. So definitely the supremum of all those is less or equal than h alpha k and infinity. Yeah. Now the fact that really the limit is the same, yeah, it's somehow hidden in this theory of measurable partitions. Yeah. So there is something to be proven there. But yeah. But intuitively is because if there was a gap here, then there would be an intermediate partition in this gap. Okay, so that's very nice though, because now computing the limit is not hard. You just literally see what's going on here, right? So for instance, well, if you do for alpha 1, so recall the following, right? So recall that h of mu is the limit of hn over n, like that. Now, it's also clear that this is the same as the limit of hn minus 1. This is just true of any sequence. If you have a subadditive sequence, right, and the limit, the drift, so to speak, exists, right? This is the same as the limit of the difference of two consecutive ones. The idea is, right, so if hn is roughly L times n, then hn minus 1 is roughly L n minus 1. So hn minus 1 is roughly L. I mean, this is just by the Cesaro average. If you take this sequence, you do the Cesaro average of this sequence, you get this sequence. Right. So that's always true. So for k equals 1, so if you do h alpha 1 given eta infinity, this is the limit as n goes to infinity of h of alpha 1 given eta n. So this is the limit of this thing of h1 plus hn minus 1 minus n hn. Right. So this one converges to the asymptotic entropy. So this one is, so in the end, you get h1 minus h mu, which means the asymptotic entropy. You can call that h infinity. So this is the first interesting fact, that if you want to know the conditional entropy between the step 1 and infinite, like, yeah, and the tail, this is the difference between the asymptotic entropy and the entropy of the step 1. So that's kind of neat, actually. And in fact, a version of this exists for each k, right? So for each, if you repeat this for any k, you get that h of alpha k minus at infinity. Well, you see, you're taking the limit here. So you have k h1. And here you say the difference between hn minus k and hn. What this is k times this. So this is k h mu. And now we go to check the independence, right? So we say that alpha k and eta infinity are independent if and only if, well, h alpha k given infinity equals h of alpha k, right? We said this. And this one is literally k times h1 minus h infinity. This one is literally k h1. Because, you know, at h alpha 1, entropy of alpha 1 is h1, and alpha k is k copies of alpha 1, because the first k steps are independent. So at this point, it's clear what happens, right? So at this point, we say that this implies, so alpha k and eta infinity are independent. This if and only if h of mu equals 0. Right. So the idea is you see you start with information, the first step of the walk. And now if you go to infinity, is there any more information that you could add so that the conditional entropy would be smaller? The conditional entropy would be smaller than this if this gives some additional information. But this is equivalent. So this difference is indeed the first step entropy minus the asymptotic entropy. And so the asymptotic entropy has to be 0. And of course, this is if and only if, because in fact, if it's true, if this is true for every k, you get this, and then you see that these are independent, right? If eta infinity is trivial, then it's independent of every alpha k, obviously. But then also, so eta k is trivial, partition is trivial, if and only if alpha k and eta infinity are independent for any k. Because again, if it's trivial, then obviously it's independent of anything. But if it's independent of all the alpha k's, well, the sigma algebra generated by the alpha k's is everything. So it must be trivial. Okay? Any questions? Okay, so now next time we will see that there will be another version of this, which is a relative version, because here we're just telling whether the boundary is trivial. But if the boundary is non-trivial, we still don't know whether the boundary is what we think it should be or not. And so that's Z station. Okay. Okay, so now before going to that, let's examine some nice class of groups that has very interesting behavior from the point of view of Poisson boundary, and these are lamplighter groups. So these are the first sort of non-trivial examples of where there is really a subtlety between whether this boundary is trivial or not. So, well, you can do a lamplighter group on any space, but we just look at the lattice. Okay. So given D, some dimension, we consider the following. So what is the idea of lamplighter? The idea is that you look at the D-dimensional grid, and you have a whole bunch of lights on it. So every site on the lattice is either on or off. So some of them are colored, and some of them are off. Okay. And what does the lamplighter do? The lamplighter can do two things. Either moves on the grid by one step, or wherever it is, it turns the light either on or off, changes the status of the light. And so let's see how to make this precise. So we say that the space, the configuration space of let's say of lights, so to speak, is just the following: is, well, let's call it KD. It's just the space of functions from ZD to Z over 2Z. So it's a function that tells you for every site whether the light is on or off, right? So this is status. This is the site. And of course, from the point of view of group theory, this is it's an infinite product of Z mod 2Z. Now there's two options. Either, yeah, all configurations could be, so there's two things. Either you could allow that there's infinitely many lights that are on, or you could also just say that only at most finitely many lights are on. And so this gives you difference between taking the product or the sum. So in fact, we say that such that support of mu is finite. So let's start with this one. So then this is just a sum over Z to the D. So you have Z to the D copies. And yeah, the plus tells you that only finitely many. So this is obviously an abelian group, very big abelian group of countable rank, but it's a nice group. But it's still abelian, so it's not the whole story. This is just the lights. And so now we need the lamplighter. So in fact, there's an action. So ZD acts on KD by translations. You can take the configurations and shift them, right? So in fact, given X in ZD and F is a configuration, we can define TXF is a new configuration. TFX of any other site Z is F of Z minus X. So we're translating all the lights by X. Okay. Okay. And now we can construct the semi-direct product. So recall that given two groups, given A, B groups with A acting by automorphisms on B, we can define semi-direct product. Right? So let's say T is an automorphism is a homomorphism from A to odd B. Then, well, we define G to be the semi-direct product. You have to never trust which way this goes, but it's one of the two that define the following, right? So we have A1, B1 dot A2, B2. Well, in the A coordinate, you just take the group operation. And in the other coordinate, well, you're acting using the automorphism. So it's B1. And then you're taking the automorphism associated to A1. So TA. And you act on B2. So the same. And so the lamplighter group is exactly this. So we are taking the action on ZD on the configuration space, and we're constructing this semi-direct product. The definition is the lamplighter group GD over ZD. So ZD is the space of lamps is exactly this ZD, and then you take it. So this group is finitely generated because at each step, as I said, we can do one of the two things. We can either move or switch lights. So the first lemma is that for any D, GD is finitely generated. Why is that? Well, again, because given, well, let's see, let's start with the generating set for ZD. Let's call it EIs. Let's say plus minus EI, such that. So standard generators for ZD, I mean, these are just the unit vectors. Okay, this is just a vector with just one in coordinate I and 0 everywhere else. So we start with the generators for ZD, and then GD is generated by, okay, let's call this S. Well, S union, and then what's the other thing we need? So okay, let's say, to be precise, we need two coordinates. So the first coordinate is in ZD, so it's plus or minus EI. 0, we don't do anything to the lights. And then the other one is, so this is for I from 1 to D. And then the other thing we need is we need one element that, again, so that doesn't do anything to the grid, but doesn't move, but just switches one light. So delta at 0. So this is switches light at 0. Yes.
Should be a marking of B1. Definition of this.
So A2 IP only one, it could be. So what's your proposal? You want to put A2 acting on V1 and then just B2?
Yes.
It's another 2. I don't know if the
It's like you acting on the right, on the left. This way.
maybe both of are equivalent. Yeah, I don't know. We can double check the definition. Yeah. So, but I think that makes sense. It's definitely you're taking one and acting on the other. So yeah. So or you can have A2 acting on B1. Yeah, I guess maybe that's also allowed. Yeah. Okay. Well, let's double check that. But so now what? So now let's see what's going on here. So yeah, so this is clearly a generating set because again, you can move around and whatever you want to switch the light at some place, you just go there. So going there is equivalent to sort of shifting the configuration space. And then you switch the light at 0. Okay, that's easy. The other thing, which is somewhat not complicated, is the growth rate. So the other thing is you want to say that GD has exponential growth. For any D. And that also is really relatively fine. So even for D equals 1, of course, if you prove it for D equals 1, that's enough. So I have a lamp lighter in 1 dimension. Right. And I want to make at most R steps, right? So let's call this S prime. Right. So you want to say what is the cardinality of G in GD, such that the norm of G is at most some big R. Well, what you can do, right? You want to switch lights. So you want to say, okay, I have R over 2. Yes.
What is the norm of GD here? It's a secondary component.
Well, the norm, yeah, it's a finitely generated group.
Right. It's how far
Yeah, so it's a finitely generated group. So let's consider this finite generating set. Yeah. So there's a number of steps in this generators. Yeah. And so you see, if you suppose you have this R over 2 support, and I claim that you can turn on any lights, you can do any configuration of lights in this in this finite chunk by at most R steps. Well, why? Oh, because you want a configuration of lights. Suppose you have 0, 1, 1, 1, something like this. Well, you start at 0, you turn on this light, then you move this you don't have to do anything. So you move again, then you turn on the light, then you move again and you turn on this light. So for whatever configuration you have on this R/2 lights, it can be reached within R steps, because we can move at most R/2 steps in the actual graph, and then we can turn on at most R/2 lights. So this is 2/R2, because because any configuration right, X F with XF with the support of F contained in 0/R/2. Okay, maybe we want to say that F is at the right side. Yeah, just that the lamplighter is here again. Otherwise, it has to go back. Yeah. So and X equals R at the end. Yeah, is reachable, is within distance R. R of 0. Yeah. So this group definitely has exponential growth. In fact, to precisely prove how big is the ball of radius R in this group, this is a really hard question. So it's not easy at all to tell exactly what is this factor here. But at least it's at least exponential. And then so this already tells us that the Poisson boundary is a difficult problem, because we don't know whether to say whether it's trivial or not. If it was a sub-exponential growth, then it would have to be always trivial. But this is not, so it will in fact depend. For instance, it depends on D what happens. So so maybe, but that we can maybe state next time. Yeah. In fact, this group is amenable, if you know what that is. So that's also another thing, because if it was non-amenable, then we would know automatically that the boundary is non-trivial. But in this case, it's an intermediate case, which is amenable group, but with exponential growth. Okay, good. Are there any questions? Okay, then I'll see you next week.